Hi, welcome to Inside Out Math. This video will be going over the geometry of doing double integrals over a general region in the domain versus the domain being a rectangle, which we've been doing in iterated integrals. Now, some recommendations before we begin is, first of all, this is a section on integration, so of course get your integration technique straight. I like to compare math to athleticism. How do you get good at sports? Say like volleyball, basketball, fencing, anything. You need to practice. How do you get good at your integration techniques? You must practice. Okay, and of course, we'll need to have a sense of geometry as well. So for single integration, the region we integrate over is just a one-dimensional interval. But for double integration, we want to be able to integrate not just over rectangles, which we've been doing in iterated integrals, but we need also to integrate over regions of any shape that is bounded, or in other words, enclosed. Okay, so let's start with the first example here is a double integral over the region D of y over x to the fifth plus 1 dA, dA being dx dy. Okay, where the region D is the set of xy such that x belongs from 0 to 1. By the way, if you haven't seen this Greek letter epsilon, this means belongs to. Okay, so the interval of x is from 0 to 1, and y belongs from 0 to x squared. Okay, meaning y ranges from y equals 0 to y equals x squared. Okay, if we want to look at this geometrically, I'll write a quick little graph here. Well, let's start with this one. Y equals 0 is this x-axis here, and I guess at y equals x squared is this parabola that goes through the origin. And if x goes from 0 to 1, here is x equals 1 here. Oh, maybe, yeah, why not? X equals 1. We're looking at, and here's x equals 0 as well. We're looking at this region D in the xy plane. So to start off, we'll need to figure out what variable we're going to integrate with respect to first. Okay, since y ranges from 0 to the variable x squared, I'm going to do that first. Okay, with respect to y, and x ranges from 0 to 1, and so we'll have a dx there. Okay, the antiderivative to y, okay, everything else is held constant. This is a partial integration with respect to y. We have y squared over 2. Y squared over x to the fifth plus 1. And we'll evaluate this from 0 to x squared dx. Okay, and we'll plug in our bounds here. We'll get a half 0 to 1 of x to the fourth over 1 plus x to the fifth dx. Okay, and this is where you'll need to be well versed in your integration techniques. I can see already that this is a u substitution. We'll let u equal the whole denominator 1 plus x to the fifth du, the differential, equals 5x dx, 5x to the fourth dx. And so dx is dx over 5x to the fifth. Scrolling down here, we'll continue. Okay, so 1/5 times half, oops, that's my phone there, is a 1/10 integral of that x to the fourth canceled, and we get 1 over x to the fifth plus 1, which is u, du. And so when x equals 0, we have u equals 1, and we also had the bound 1. When x equals 1, u will equal 2, right? 1 plus 1 is 2, okay? And so we'll get 1/10, not 2, but 10. The antiderivative of 1 over u is ln absolute value of u, evaluated from 1 to 2. Okay, plugging in our value or our bounds our bound from 1 to 2, we get 1/10 ln 2. And here is our solution. And for our next example here, we'll go ahead and do this double integral over the region D of x squared plus 2y dA. And D is bounded by y equals x, y equals x cubed, and x is greater than or equal to 0. Alright, so we're not given a whole lot of information about our domain of integration, meaning where we plug our bounds, okay? So we're going to have to do some investigation by drawing the domain of integration given this set of information. So let's go ahead and draw our axes here. Okay, let's draw y equals x in pink here. Y equals x. And we'll draw y equals x cubed in, I guess, orange here. Let's go free draw. Oh, that's not a very good one. Oh, I'm missing the origin. There we are. And x is greater than 0. We'll just take all of this region here. And now I guess the region that includes y equals x cubed, and x is greater than 0 is this little tiny region here. Okay, and where do those regions meet? Well, I think it's 1, 1. Okay, and we can prove it by, well, y equals x meets y equals x cubed at this point here, so we can equate x and x cubed together. Okay, and divide by x, we get x squared equals 1, so x equals plus or minus 1. And the other point that they meet is when x equals -1 there. And, oh, that should be a -1, not an x. Okay. And a height of what? When, oh, let's just take this guy. When x is 1, y is 1 as well. So we can choose to use vertical strips or horizontal strips depending on your preference. I'm going to say let's do vertical strips, meaning the top curve, the upper curve minus the lower curve here. Looks like the upper curve is this pink y equals x. So we'll go ahead and evaluate the double integral from y equals x to y equals the orange x cubed. Actually, I should say it the other way around. X cubed to x. And so the x interval is going to be from 0 to 1 of x squared plus 2y. And since we did vertical strips, we'll go dy dx. Okay. And now integrate with respect to y. Well, that's my phone one more time. The antiderivative to x squared with respect to y is x squared y plus 2y squared over 2, or y squared. Okay, and we'll evaluate this from x cubed to x. And remember, we're replacing all the y variables. Okay, and we'll get the integral from 0 to 1 of, I guess, a x cubed plus x squared minus, oh geez, x to the 5th minus x to the 6th. Oh geez. Okay, a little bit annoying. That's fine. Scroll down here. And antiderivative will be x to the 4th over 4 plus x cubed over 3 minus x to the 6th over 6 minus x to the 7 over 7. Okay, evaluate this from 0 to 1. And we have a 1/4 plus a 1/3 minus a 1/6 minus a 1/7. And I'll get a calculator here. Really don't want to do this. 1/4 plus 1/3 minus 1. Oh, my phone is going crazy right now. This should be a minus 1/7, and that should equal 23 over 84. And this is our solution. And for the third and last example of this video here, we'll go ahead and take the double region over the domain D of 2xy dA, where D is the triangular region with vertices 0, 0, 1, 2, and 0, 3. So again, we're not given a whole lot of information of what we can plug into our upper and lower limits of dx dy. So we'll have to draw this out and see what happens. Okay, so it looks like we have the point 0, 0 here. Let's go ahead and scale this a little bit. That'll be 1, 2, 3. Oh, sorry, maybe I'll do it this way. 1, 2, 3, and this will be the point 0, 3. And 1, 2 will be about, I guess, right there. And we'll call that 1, 2. Okay. Let's change our colors here, and pink there, and maybe we'll do orange here, and leave the white as this y-axis here. I'm going to label our axes, y and x. Okay, so what would be more appropriate is the question, vertical strips or horizontal strips? Now, if we did vertical strips, or maybe let's start with horizontal strips, looks like we would need to do two integrals at the same time. We need to account for the upper and lower curve from white to orange here, and also the upper curve and lower curve for the white and pink. Okay, so I think vertical strips is more appropriate because we have one set of upper and lower curve, the orange being the upper and pink being the lower curve. Okay, but what are these curves is the question. Okay, so it looks like for the pink here, we'll have a intercept of 0 and a slope of 2x. Okay, and for this orange curve, we'll have y equals, I guess, a intercept of positive 3 and a slope of, let's see, 2 minus 3 is a negative 1 over 1, so it'll be a negative x here. Negative x plus 3 is this upper curve. So let's go ahead and solve this here. Upper curve minus lower curve, negative x plus 3 to 2x, okay? And x ranges from 0 to 1. 0 to 1, okay? Of 2xy, and since we're doing vertical strips, dy dx. Antiderivative of xy with respect to y is, or xy I should say, is a xy squared over 2 xy squared, and it looks like this thing will cancel here and evaluate from 2x to negative x plus 3 dx. We'll go ahead and plug in our bounds. Get x multiplied by, oh, this one's going to be a long one, a negative x plus 3 quantity squared minus a 4x squared dx. Let's combine like terms, continuing on this side. Integral from 0 to 1 of x. Looks like we have a x squared minus 6x. This is a difference of squares, that's why I'm doing it. Or not a difference of squares. Whatever this. It's 9 minus 4x squared dx. Distribute from 0 to 1 of x squared minus 4x squared is a negative 3x squared, so we'll get a distribute the x over, negative 3x cubed minus 6x squared plus 9x dx. Okay, and Antiderivative of negative 3x cubed is a negative 3x to the fourth over 4 minus 6x squared, it'll be a 6x cubed over 3, or 2x cubed, plus 9x squared over 2. Evaluate this from 0 to 1, and we'll get a negative 3/4 minus 2 plus 9 over 2, and we should get, on my calculator here, negative 3 over 4 minus 2 plus 9 divided by 2. This looks about right, and we get 7 over 4 as our solution. Okay, so that's the end of this video. Thank you for watching. Subscribe and have a nice day.